We're going to finish up the thermodynamics video today. I don't remember exactly where I stopped, but that's okay. If this is overlap, perfect. Delta G, Gibbs free energy of reaction, or the change in Gibbs free energy of reaction, is a concept that's so important in terms of the rest of our material, depending on your understanding of it or your understanding of the rest of the material, depending on this, that it's worth repeating. So let's go back and talk about what the change in Gibbs free energy of reaction is. You calculated it back in general chemistry. And what you did was you went to a table in the back of your Gen Chem book, and the table had the energy contained in different molecules. So you looked up the energy contained in the products, and the little table had, everything in what felt like a 2-point font. Then you looked up the energy contained in the reactants and you did products minus reactants. So let's think about that for a minute. So we had a couple of graphs when we were doing enzymes. We had energy on the y-axis. We had reaction progress on the x-axis. So as I go along the x-axis, my reactants are becoming the products. So I don't remember which way we drew it, which one had more energy, doesn't matter, because we were looking at what was going on in the middle of that reaction. Now we don't care. And the reason I'm saying we don't care is that delta G is independent of the path of reaction. So delta G is independent of the path of reaction. We don't care what's going on in the middle. Delta G, remember, is your go or no-go measurement. It's looking at the energy contained in the products versus the energy contained in the reactants, and that's it. So let's look. Let's do the first graph. I have more energy contained in my reactants up here than I do my products. So if I do products minus reactants, I'm going to have a little number minus a big number. That's going to give me a negative delta G. That means the reaction is going to go, because what I'm doing overall, if I look at products minus reactants, is I drop. I need to get from a higher energy to a lower energy in in the course of doing my reaction. I can do that. So I'm going from a higher energy to a lower energy. That's doable. So intuitively, that's usually okay. Intuitively, though, however, this negative delta G usually isn't okay. So that's why I do it this way, saying, well, I'm going from a high energy to a low energy. Can I do that? Well, yeah. But because of the equation, the calculation being done is products minus reactants, that gives us a negative number. So a negative delta G is our go. A reaction with a negative delta G will go. Don't forget, though, this word spontaneous. The word spontaneous can mess you up. In everyday language, spontaneous has the implication of speed, fast. You make a spontaneous decision. That implies you made a quick decision. Don't forget, in chemistry, spontaneous just means I have enough energy contained in these reactants to get me to the product. That's it. So it just means the reaction is going to go. If now the other way around, the products have more energy than the reactants, when I do products minus reactants, I'll get a positive number. But to get from reactant to product, I've got to climb up an energy hill. I need more energy for the products than I have contained in the reactants. So because of that, it's going to be my no-go. So if delta G is positive, I positively have to put energy in to get from those reactants to the products. Then, after we do all that, the one that you tend to forget, and it's just a losing the forest for the trees thing, Is delta G equals 0 for a reversible reaction? So the products and the reactants contain exactly the same amount of energy, so products minus reactants equals 0. That's just controlled by equilibrium. So whether it goes or doesn't go depends on whether you're in equilibrium, the whole Le Chatelier story. So that's your delta G. So delta G is negative. That's going to be my go. Positive is going to be my no-go. Equilibrium determines whether my delta G equals 0 reaction goes. If I'm in equilibrium, I have nowhere to go. I'm in equilibrium. If I'm not in equilibrium, my system will adjust to go to equilibrium. So again, delta G is independent of the path of reaction. Enzymes are all about the path of reaction because enzymes make the path of reaction easier. Since delta G is independent of the path of reaction, it tells you nothing about the rate of reaction. Where enzymes are all about the rate of reaction because an enzyme makes the rate of reaction easier, and as a result of the rate of the makes the path of reaction easier. As a result of the path of reaction being easier, it allows you to increase the rate of reaction. Okay, so let's talk about ATP. We said we have a couple of definitions, catabolic and anabolic. Catabolic reactions are big catastrophes. I'm breaking big molecules down into little molecules. An anabolic reaction is taking little molecules, putting them together, and making big molecules, or building up cells if you're applying the concept to cells. All metabolic processes involve energy. All metabolic processes are made up of reactions, different reactions. Some reactions produce energy, as in energy exits, and those are exergonic reactions. Some require energy to go in. If energy needs to enter, it's endergonic. So a reaction that needs energy needs it to enter, endergonic. If energy exits, as in you produce energy, it's exergonic. Don't cross these two sets of definitions. I'll hear you guys saying, well, all catabolic reactions are exergonic. No, some catabolic reactions are exergonic. Or anabolic is endergonic. Can be, sometimes. We're going to do catabolic delta G equals 0. Anabolic delta G equals 0. Um, we're going to have some of everything. So keep these two definitions as one set, these two as another set, and don't try drawing parallels between them. Okay, so ATP is our biochemistry money. I know you guys hate my money analogies, but everybody thinks in money. So whether you hate my analogies or not, you think in money because you have to manage it. So we're going to use money. Biochemistry is, or ATP is our biochemistry money. So we talked about ATP a little bit before, and we looked at what it's made up of. I have my ribose, and if it's ATP, I have an adenine. An adenine and a ribose put together form adenosine. So my molecule is adenosine triphosphate. And let me remind you again, be comfortable with the abbreviation. We're going to use it. Be comfortable with the name spelled out. In case you see that in a question, you might be looking for ATP as an answer, and you don't get offered ATP. You get offered adenosine triphosphate. So be comfortable with either. So we'll also have molecules like CTP, where instead of adenine, I'll have a cytosine. GTP, I'll have a guanine. UTP, I'll have a uracil. Recognize that those are different molecules. However, they work the same way because the part we're concerned about is actually over here, these three phosphates. These three phosphates are the business end of the molecule. So let's talk about that. Right now, I have three phosphates on here. So it's ATP, adenosine triphosphate. But I can do something. I can break this high energy phosphate bond. That'll take my ATP to ADP plus a phosphate. But it's a plus something else that we don't tend to write, but the something else is the important part. Plus energy. So I could take that phosphate off. And what I'm doing when I take that phosphate off is I'm breaking a high energy phosphate bond. High energy phosphate bond, the energy being the big deal. So I just got energy now from doing that, and I can go and use this energy to drive another reaction. Then I have my ADP. I can break another high energy phosphate bond. I'll get AMP plus a phosphate plus energy again. So I might use the phosphate for something, I might not, but I'm absolutely using the energy. So what I want you guys to get very tuned into is this. You see ATP going to ADP, this part of it, oh, I must have needed energy for something. We will one time see ADP going to AMP. I still needed energy for something. So it's like when you're shopping and you're looking at price tags, you find something in the store and you like it, and then you look at the price tag and you decide, well, do I still like it? Is it worth that? Is it not worth that? But you're using that price tag to look, it's part of your equation. This is like a price tag. I see ATP getting used. Here's my price. I needed energy. So it's the same idea. You're gonna get really keyed into looking at reactions. If I see ATP getting used, oh, I had to pay for that reaction. Then let's flip this around. If I'm down to say, well, let's do the one we typically do. If I have ADP and I want to go to ATP, I need a couple things. One thing I need is a phosphate. All right, whatever. That's easy. We usually have those hanging around. Another thing I absolutely need is energy. I'm not getting from ADP back to ATP without energy. I'm not getting back without the phosphate either, but we usually have that. That's pretty easy. But energy, maybe, maybe not. So here's how you get that energy. You eat whatever you eat, your food, your fuel, and you'll probably look at what you ate. I just ate 200 calories of whatever. You're going to go through the steps, the reactions, the processes that we haven't done yet. But you're going to take those calories, because calories are really just an energy measurement. We can measure calories in peanut butter Oreos, or we could calculate how many ATP are in peanut butter Oreos. The food industry might not quite go for that, but we could do the food label that way too if we wanted to. So those calories are an energy measurement. So I'm going to use those calories to replace this energy and get back to ATP. So just like the price tag analogy, you're going to get very tuned into, oh, do I have enough energy? I want to make an ATP. Let's look at what I have. What energy do I have from where? Do I have enough to make this high energy phosphate bond and put a phosphate back on there? If I do, great. Let's do it. If I don't, what am I going to have to do that? So that's what I mean by ATP is kind of like a price tag. You're looking at, like when you go shopping, you look at lots of stuff, but you look at price tags. So when you're looking at reactions, you look at lots of stuff, but you're going to look at, am I using ATP? Oh, I'm paying for that reaction if I am. Am I making ATP? Oh, I've got some energy from somewhere to make that high energy phosphate bond. I have the energy to do it. So I'll keep hammering you on that. but you're going to get tuned into that to keep track of, know what's going on. Here's the other thing with these high energy phosphate bonds. Not all bonds are created equal. So again, I'm using the money analogy. I was going to say, please don't email me. Email me if you want. I'm going to use the money analogy. And rather than putting an energy value on the bond, again, we think better in money. This high energy phosphate bond, let's say I get $10 for breaking it. This one, let's say I get 5. My proportion's roughly correct. My numbers aren't. So here's what you could do. You can go from ATP to ADP to AMP. And let's look at how much money I get for doing that. Try to die, I get $10. Die to mono, I get $5. So I get a total of $15 for doing that. Okay, whatever. Now let's go back. If I'm going ATP to ADP and I get $10, what if I can do that twice? So, oops. Oh, darn it. All right, so the other one was $15. ATP to ADP, we said that's $10. What if I can go 2 ATP to 2 ADP? That's a better deal, huh? So that's a better deal. For that reason, what you're going to see us doing in our reactions is most of the time try to die, find the energy to replace the bond, back to try. When we need energy, try to die, die back to try. Only one place in everything that we're going to do that I can think of now will we actually go to mono. So most of the time, it's going to be try to die, get the energy, then die back to try when we have the energy to replace it. So most commonly you'll see that because it's just more efficient than going over to this other bond. Oh, I just moved back a slide. I thought I lost it. Okay. No matter how much room you give me to write, I want more. And there's the structures. We have our 3 phosphates, take one off, down to 2, take one off, down to 1, and we won't go past that. Okay, real numbers if you would like them rather than my $10 and $5. Little disclaimer. You're always, always, always going to see a large overall negative delta G in any process that we're going to do. And let's go back and do that. I don't remember if the other video cut off before we got there. So let's talk about delta G of the process. And again, if it's review, I guess if it's a review and you don't need it, fast forward me. I have my little metabolic process, A going to B, going to C, D, going to F. So let's put some delta G's in here. Delta G is plus 10. Let's make this an equal 0. Delta G equals, I don't know, minus 25. Delta G equals, let's do a plus 5. So my question for you is this. Will this process go? I don't know. Let's figure it out. So we're going to look at our overall delta G. So here's how we get this. We add it all up. Plus 10, plus 0, plus minus 25, plus 5. So what do I get? I get a minus 10. So my overall delta G is minus 10. And I didn't put units in because we're not actually going to do the calculations, so they're not important right now. So my overall delta G is a negative. Perfect. Great. That means the process is going to go. Well, how can it go? I've got this plus and this plus. It's kind of like you in your office in a month. First week of the month, You might have paid all your bills. So here you had a bunch of bills due. You paid your light bill, you paid your phone bill, you paid whatever. So that the actual money you looked at in versus out in your office was a negative number. So not so good. Next week you paid some bills, so you were flat. Third week of the month, bills are paid. Every penny that came into the office that month, you kept. It went into the account. You didn't have anything to pay that month. Last week of the month, you did payroll again. So, how hung up are you getting on these 2 weeks of the month that were negative? Well, it depends. You're going to look at the positive one. If overall you're positive, good. You're good. Perfect. Same thing. So, what did we do? This really good week of the month carried along the two that weren't so good. The negative delta G has enough energy to carry along the two that were positive. So I had enough extra energy here to cover this and cover this. So as long as my overall is negative, I'm good. So I have an overall negative delta G of -10 from the negative reactions dragging along. You'll hear that term, a little casual, but you'll hear it, carrying along the other reactions. So same as your budget in the office. But you always need a negative something. We can't cut it right to zero. And here's why. All of these numbers are theoretical numbers. So keep that in mind when you're looking at cutting it really, really close. It's kind of like if you just bought a new car that the window sticker says gives you 30 miles to the gallon. You know darn well if you put 1.000 gallons of gas in that car to drive 30 miles, you're going to be pushing the last 2 miles. So that's a theoretical number under ideal conditions. Same thing with delta G. Theoretical number under ideal conditions. Your cells are not ideal conditions. So my negative delta G, that's the maximum I might possibly get, but I probably won't. My positive delta G, that's the minimum amount of energy that I can put in to get that reaction to go. Probably need more than that. And again, remembering your spontaneity thing. Spontaneity is just saying the reaction has enough energy contained in those reactants to become products. Let me say it again. Delta G is independent of the path of reaction. Enzymes are all about the path of reaction. They make the path of reaction easier by lowering the activation energy or lowering the energy of the transition state, allowing you to increase the rate of reaction. So be very, very careful if you happen to get an enzyme question and a delta G question back to back, especially if they're focusing on rate, spontaneity, things like that. That's the perfect storm of getting you to mess up a question. So be very careful about keeping the concepts separate. Okay, we're always making and breaking ATP, even though we'll be focusing on one or the other, whichever we're doing at the moment. We'll have a time frame in there. We'll come to that. Okay, we talked about this in class. We'll talk about what molecule can be converted to what molecule, which ones have more energy, things like that. And ATP is really what we're coming down to with all this. This was the conversation in class the first day or two. I said to you, which one has more calories, a fat or a protein? And all you guys very intuitively, very quickly said, a fat, of course, a fat. And that's intuitive, everyday knowledge. What we're going to do is look at the number of ATPs produced by a carb, the number of ATPs produced by a particular fat, and you'll look at that and compare it to prove it to yourself. So it's kind of interesting. So we'll get to that. Okay, there are 6 different chemical reactions we're going to do in the whole course between now and the end of second quarter. So we're going to go over those now, and a lot of reactions will fall into more than one category. But this is the talk in off the ledge conversation that I'll send you back to a few times. Because we're going to do these 6 reactions, but we're going to do them over and over and over on different molecules. So your tendency is to focus on the molecule and what it's becoming and all that, and overlook that it's doing the same reaction that you did on another molecule exactly the same way, and another one and another one. So this is where I'm going to chase you on paying attention to the trends, because no concept in this class is difficult. Really, no concept in this whole program is difficult. There's just tons and tons and tons of the concepts for you to learn and know, and that takes time. So 6 reactions, we'll go through them, and you'll just do them over and over. Okay, so the first reaction we're going to do is oxidation and reduction. So you did that in general chemistry, and you've had lots of time to forget it, so we're going to start from the start with it and get pretty basic with it. So oxidation is losing an electron, reduction is gaining an electron. So one of the little mnemonics to remember it is an oil rig. You have an oil rig. Oxidation is losing. Reduction is gaining. So here's the thing with oxidation and reduction. I can't have a molecule lose an electron without another molecule gaining an electron. I can't have a molecule gain an electron without another molecule losing an electron. Differently than, say, our phosphate or carbon dioxide or whatever, I can't take an electron off and just leave it hanging out somewhere. I don't have electrons hanging out somewhere to just put on something. So they've always got to get handed to another molecule. So oxidation and reduction then always have to go together. So we'll hear the expression, it's a redox reaction. It's the combination of the two, one molecule losing an electron, so another molecule is gaining the electron. So the way we can tell in a lot of cases which way we're going is by oxidation state or oxidation number. So I can have, the first example we did was iron. I can have the ferric, ferrous, whichever form of it, 2 plus or 3 plus. So my oxidation state or my oxidation number is like a net worth. So if I go from a 2 plus, put a negative thing on there, don't forget an electron's a negative thing, and my 2 plus gains, I went the wrong way, darn it. I'm not starting the video over. So let's do it this way. My 2 plus loses an electron. So I lose an electron. I'm going to go to 3 plus. My net worth just increased because I lost that negative thing. So that's like the analogy we did in class. We said that, I don't know, Palmer lost all your paperwork for your student loan, so you got a free quarter or whatever. What happened to your net worth? It went up because you lost a negative thing. Or the other way around. Let's say your net worth right now is the 3 plus. You just sign up for another quarter and you gain an electron. You gain something. So intuitively, it's a little backwards than what you would think. You gained something, but your net worth, your oxidation number or oxidation state just went down because what you gained was a negative thing. So your oxidation state or your oxidation number is your net worth. So here's the thing with an electron, and this is where we apply it, where it applies to us. The electron travels with the proton. An electron and a proton make a hydrogen. So for us to tell what's going on, we're going to chase the H's, chase the hydrogens. So we're going to have a couple of molecules. We're going to have a molecule called nicotine adenine dinucleotide. We'll talk about that. It's a niacin-based molecule. It's a molecule called an electron carrier. Got another riboflavin-based electron carrier we call FAD. So what we can do is we could put electrons on them. We can convert NAD to NADH. We can convert FAD to FADH2. Here's my electrons. So since I gained my electrons going that way, I put the electrons on. That was my gain. Oil rig. Reduction is a gain. So these two reactions are reduction because I gained the electrons. I can also go the other way around. I can go from NADH to NAD. I can go from FADH2 to FAD. Well, chase my H's. Where are my hydrogens? Here it is, gone. Here it is, gone. So I lost my electrons. Oxidation is losing. So there's my oxidations. But we said I can't have an oxidation without a reduction. I can't have a reduction without an oxidation. I can't have somebody gain an electron without somebody losing it. I can't have somebody lose it without somebody else gaining it. So we're always going to see the reactions written like this. So let's do a reaction that's a very common reaction we're going to see a lot of different places. I can have a molecule called malate, and we'll get into the structure later, going to a molecule called oxaloacetate. For malate to go to oxaloacetate, NAD goes to NADH. So my question for you is this, right off. What kind of reaction is malate going to oxaloacetate? Well, I don't know. You said we're not even going to do the structures of them for a while. But you do know. And here's why you know. Where's my hydrogen? It's right there. Okay, so what's this reaction doing? Going from no hydrogen to a hydrogen. Oxidation is losing, reduction is gaining. I gained it. So this has to be my reduction. I can't have a molecule gain an electron without somebody else losing an electron. I can't have a molecule lose an electron without somebody else gaining it. This has got to be my oxidation then. So what happened here, and you can't tell without the structures, and we're going to do all the structures. They're going to be in every PowerPoint, everything. When I said that I'm not going to ask you about them, what I mean by that, and allow me to remind you again, I'm not going to draw the structure and say name it, and say draw it, but you absolutely have to know what's going on in them to know what's going on. So that H, that hydrogen, has to have been on the malate. Now it's over here. So the malate lost it. When it lost it, it became an oxaloacetate. When NAD gained it, NAD became the NADH. So this is pretty cool because what's really going on here is an energy transfer. Malate had a certain amount of energy in it. Oxaloacetate has less. So from going from malate to oxaloacetate, we lost energy because the energy went on here. The NADH then is going to go and make us ATP, which is pretty cool. So let's do another one. Actually, let's just turn this reaction around. I have oxaloacetate. I'm going to abbreviate it, going to malate. To do that, NADH has to go to NAD. So what's going on here? Again, chase the H. So I'm looking at NADH going to NAD. We lost an electron. Oxidation is losing. Then oxaloacetate going to malate had to be the reduction. So what I just did, took the energy off the NADH, put it on the malate. So we'll do this reaction several times over. So that's why I chose this one to just show you. What's interesting though with this is this. With this one, we wrote this reaction, what's going on with the NAD and the NADH, in a very by the way form. And it makes the malate going to oxaloacetate look like the more important part of it. And really, neither one's more important than the other. What tends to happen is we'll have a process, A going to B, going to C, going to D. And you have to know that. You're going to get asked about it, whatever. So malate to oxaloacetate might be, B to C or whatever, one of the steps. We tend to focus on that because it's, one of the steps. I might get asked the step before, I might get asked the step after, whatever. And it takes the focus away from like NAD going to NADH or whatever. And in a way, that's kind of the more important part in terms of energy. I just made that high energy molecule. So my point is, just because a reaction is written in this kind of by the way thing, don't minimize the importance of it. We could have written it, and I think it's just more unclear. We could have gone, malate plus NAD goes to oxaloacetate plus NADH. And I think it's just more cluttered doing it that way. I think separating it like this lets us see, here's the reduction, here's the oxidation more clearly. But it's up to you, however you want to write your notes. I just want you to realize just because we write something over the arrow, it's not minimizing it. Okay. Next kind of reaction we're going to do is chemical ligation. So you probably won't really pay attention to the name ligation again, and that's okay. But this is where I was saying pay attention to ATP. If I'm breaking an ATP, I want the energy. Might use the phosphate, might not. So here's pyruvate. We haven't even done that yet, going to oxaloacetate. But you can already look at this reaction and say, oh, I need energy to get there. Here's my price tag. I broke the phosphate off, didn't do anything with it. Got an ATP in the phosphate, but I know I needed energy to get here. So this is the kind of the look at the price tag example. If you see it going the other way, and this is actually a reversible reaction, if you see it going the other way, so I'm going this way, you're going to say, oh, I was able to make an ATP, so I had to have an ADP and a phosphate, easy, but I had to have had the energy to put that back together and make the ATP. So again, kind of like looking at price tags when you're shopping. Okay, isomers, really easy. I'm not adding or taking away anything, but I'm rearranging the molecule. So I might have, say, glucose, C6H12O6, and I might rearrange that into fructose, C6H12O6. If I just look at what's in there, it looks like I did nothing. I had to tell you it was glucose going to fructose because I didn't add or take away anything. So when I do this, most often, I shouldn't say most often, often spontaneous, or it just could be delta G equals 0. So pay attention when we're doing it to the reasons. It might be a delta G equals 0 and we just do it. Or it might be sometimes setting up for another reaction. And I bring this up for the organic chemists. In organic chemistry, you're always going from a less stable molecule to a more stable molecule, at least in test questions. So you're always looking for the next step to be more stability, more stability. Sometimes we're going to go the other way. Sometimes we don't have enough energy contained in the molecule we have to make the one we want to make. So we'll add an extra step, go to a less stable, as in more volatile or more reactive molecule that will go to that product with less energy. So we're going to do a lot of isomerizations very often to try to get over an energy barrier, deal with a limited amount of energy that we might have. Okay, group transfer. We're going to move functional groups a lot. The functional group might be the phosphate. I took a phosphate off of ATP, it gave me ADP, put it on the glucose to give me glucose 6-phosphate. So very often phosphates are the functional group we're going to move. Sometimes we're going to move hydroxyls. Sometimes we'll move other groups, but those are the two big ones. So when we're looking at those, we're going to talk about the why. Might be an energy thing, might be a volatility thing, which really is an energy thing too. So we'll talk about the why to make it more relevant. But you'll see a functional group, not one hydrogen or whatever moving. You'll see something with it. Okay, hydro something reactions. There's two of them, so let's talk about them. First hydro something reaction we're going to do is hydration. So the reaction is hydration, and we're very often going to see hydrations separating two oxidations. So I take my water molecule and I split it. I split it into an H and an OH. I have another molecule, the double bond somewhere in it. So what I'm going to do is this. I'm going to open up this double bond, as in I'm going to get rid of the double bond. What that allows me to do is attach the hydrogen to one side of the double bond and the hydroxyl to the other side of the double bond. So I split the water molecule, put part of it on one carbon, part of it on the other carbon. So now most frequently I'm ready to oxidize again. I can also dehydrate. And in dehydration, what I'm going to do, take that hydrogen out of there, send it to a water, hydroxyl out of there, send it to a water, put an H and an OH together, and I can put my double bond back there. So I'm going to hydrate, I'm going to dehydrate. Then the other thing I can do is this. I can do hydrolysis, hydrolysis. Lysis, remember, is breaking. So I've got my H and my OH, my water. I have another molecule. Whatever it is. So what I'm going to do is this. I'm going to split it. Lysis is splitting. So then I'll take one side and I'll put the hydrogen on it. I'll take the other side and I'll put the hydroxyl on it. So I actually split the molecule. So here's where this can get sticky. Some of the board reviews teach look for the word split to tell what kind of reaction it is. If somebody wants to mess with you, they'll say, I split the water. They did. Look at what's going on with the other molecule. If I'm doing something with a double bond, that's going to be my hydration. If I'm splitting the other molecule, the one I'm hydro something in, that's going to be my hydrolysis. If you get asked Anything else, hydrogenolysis, whatever, it's not. The reactions we're going to do that you're going to get asked about are going to be hydration and hydrolysis. Don't worry about hydrogenolysis, whatever that is. It's nothing we're going to do. Okay, we can add functional groups. We can take away functional groups. Don't worry about the enzyme yet. So we're going to add them. We're going to move them. We're going to take them away. We're going to talk about them as that unit that is the functional group, and we will review functional groups. And for you guys who haven't done them, you'll learn them and you'll know what I'm talking about. Group of atoms put together in a particular arrangement. We give that arrangement a name. So we move that little arrangement either onto a molecule, off of a molecule, or whatever. Okay, we ended when we did this with this diagram. And I did it for shock value. But I wanted you to realize and look, the shock value is, these are all things we're going to do. And it looks like a lot of stuff here, but it's really two reactions. We're either doing oxidation reduction or hydration dehydration. So in this whole thing, there's two reactions. So this whole row and this whole row, that's all oxidation and reduction. Then in the middle, separating them, is hydration or dehydration. That's it. So my point is, when you see something that looks as big and ugly and messy as this is, slow down for a second. This is the first talking off the ledge speech. But slow down for a second and look at what's really going on. You have to know two reactions here to do this, and that's it. And that's very often going to be the case when it looks like lots and lots of reactions.